Okay. Hi.
Great. So thanks for being here, everyone. Today is the pathway presentations for the two areas, the physical electronics and photonics area, and then the power area is next with that will be Professor Meng Wu. But we will get started with Professor Trevor Thornton for the physical electronics and photonics area. And students, if you have questions, please add them to the chat feature, and we will moderate those at the end. So please take it away, and thanks for being here, Professor Thornton.
You're very welcome, Bob, and thank you to you and Cheryl and everybody else for organizing this. And thanks to all the students for showing up in the Zoom room today. And my name's Trevor Thornton, and I coordinate our activities in the physical electronics and photonics area. So I'm showing you this picture of the Waymo car, and I'm sure if those of you who spend any time on or near the Tempe campus, you'll see these things driving themselves around all the time. So it's kind of remarkable, self-driving, driverless car. And it's a good example of how physical electronics and photonics, bit of a mouthful, right? Physical electronics and photonics. So we go by the acronym PP, but the Waymo car is it is a good example of how this kind of electronics and photonics systems are everywhere in our daily lives, right? So the Waymo car exemplifies, let me spend a few minutes to get my laser pointer. Here we go. So the Waymo car, self-driving cars, electric vehicles in general personify how electronics and photonics are used in power systems, radar communications, computers, of course, and then in all the control systems involved in something like this. So if you look at it, it's got this bazillions of sensors right at the top. This thing at the top is a LiDAR. So it's like a radar system that scans around and detects for obstacles. It's basically I like to tell everybody, it's basically a battery powered supercomputer on wheels. So the supercomputer, of course, full of electronics. The power systems are kind of remarkable. Tens of kilowatts of stored energy, multiple tens of kilowatts of stored energy, all being transferred backwards and forwards between regeneration, charging system, the electric motors that are involved. So it's kind of remarkable system. So we've come a long way since the original electronics based on vacuum tubes, right? And then this is the first transistor. So this is for those of you who have done 352 or 436, this is a germanium bipolar transistor. So they took a slab of p-type germanium, connected to a slab of n-type germanium, and then poked it into a slab of p-type germanium. And they were able to show transistor functionality here back in Bell Labs, back in the sort of 50s. Then Texas Instruments demonstrated the first integrated circuit. So look at this thing. Again, you can see wires connected. You can hold this in your hand. You can build this in the lab. And then IBM mainframes, and then the Mac. So, this is all 1980s vintage, so 40 years ago. And so now we've come to this point where, solar power is prevalent everywhere. Very sophisticated integrated circuits. I'll talk a little bit more about this, but both for digital circuits, so basic VLSI processing for just computer horsepower, but also sophisticated RF microwave systems. So this is basically an RF microwave power amplifier integrated onto a chip. And once upon a time, this whole thing took a sort of a lab bench to build. Now you can integrate it onto a piece of silicon. Tablets, of course, the cars, self-driving. So lots of things going on here. And it's all been enabled by this, what has come to be known Moore's law, right? So Gordon Moore, back in the early 70s, recognized that the number of transistors on a chip was doubling roughly every 18 months. Now, we call it a law, so it's not a law like F equals ma, Newton's law of motion, but it's sort of an empirical acknowledgement of the fact that the number of transistors double. So this graph ends at 10 in 2020, so it's still going on. Here's a more recent one from Intel, projecting that by the time we reach 2030, we'll have 1 trillion transistors on a chip. Think about that, 1 trillion operating transistors on a chip, so kind of remarkable. All right, so to be successful, if you want careers in semiconductor manufacturing and related industries, and I keep telling my graduate students, it's a great time to be working in semiconductors. So if you are interested in a career in that field, then, number of things we need to know. So we need to have some understanding of device physics, and, our sort of introductory course there is EEE 352, Properties of Materials, where we learn about metals, insulators, and semiconductors, and how current flows due to the motion of electrons and holes, and all that stuff. So we need device physics. We need to know how those integrated circuits I mentioned are fabricated, right? The expensive clean room facilities that we build to fabricate them. How do we design those circuits? And I'll talk some more about that. And then modeling and measurement. So lots of background material that's needed, and we cover that. So let me go back. I'm here representing physical electronics and photonics, and we have this suite of courses that I'm going to talk about in a few moments. But the School of ECE, we like to emphasize both depth and breadth, right? So depth is you choose a technical area, your technical elective, and you do the classes that cover. So I'm talking about depth now, right? So you understand the subject in some detail. Yeah, in some detail. But also, we want breadth. So, I would encourage anybody who's interested in physical electronics and photonics to, look at the circuits classes that are offered, because, if you have a good understanding of how transistors are made, well, you also need to know how they're used in real circuit design. So both analog, mixed signal, digital circuit design. Likewise, if you're anybody there in the circuits track, it's important that you understand how the transistors are made when you lay them out using your process design kits. So make sure you cover here. I'm going to be talking about depth, but make sure you look at the breadth as well. All right, so these are the senior level classes that we offer that are foundational for the PEP area. So look at this, quantum mechanics. I don't know, how many of you saw Oppenheimer, right? That movie addressed the beginnings of quantum mechanics and how it influences our life. When I was a student a long time ago, quantum mechanics was really the purview in the area of physics. But now, our cell phones, our lasers, everything that we use in a day-to-day experience relies on the fact that quantum mechanics is now fairly well understood. So we offer this foundational class in quantum mechanics for engineers, and it's becoming more and more important for engineers. So there will be changes coming down the pipeline where we talk about quantum systems and quantum computing and quantum information. But for now, it's underpinned by quantum mechanics. Then the class I'm teaching currently, now offered in both the fall and the spring semesters, is Fundamentals of CMOS and MEMS. So CMOS, complementary metal oxide semiconductor, that's the workhorse for the semiconductor industry. MEMS, micro electromechanical systems. When you rotate your cell phone, can you see my cell phone? When I rotate it, the orientation of the display changes because it recognizes that there's been some motion, some acceleration, and so we have these micro electromechanical chips as part of our cell phones, crash bags in our cars. The prerequisites, well, I guess the co-requisites to be successful in this class, we need to understand 352, and then it helps 436, Fundamentals of Solid State Devices. This is the follow-on class from 352. 352 teaches you, as I mentioned, the basics of metals, semiconductors, and insulators, finishes up with PN junction diodes. 436 takes those ideas and builds on them to understand how transistors work. And so again, 435 helpful if you're taking, or you will be taking, 436 to understand how solid state devices work. So then the sort of sister course to 436 is 437, optoelectronics. So while 436 explains how transistors, electrical devices work, 437 explains how their optical counterparts work. So like light emitting diodes, semiconductor lasers, photodiodes and detectors. So again, these are very important for the high-speed communication systems. Then 439, semiconductor facilities, clean room practices. This is how do you design and build a clean room that you use to make these semiconductor components. So again, here in the Valley, I don't know if any of you have driven on I-17 recently on the West Valley. If you look out towards the west, you'll see all these cranes where they're building TSMC's factories. So clearly that's a big investment here locally and also nationally. And then ASU, we have a lot of strengths in PV, photovoltaic, so solar power energy conversion. So 465 stresses the science behind this, as well as the manufacturing and economics of producing highly efficient solar cells. So maybe I'll pause there to see, Bob, if there have been any relevant questions in the chat.
No questions in the chat yet, but students, please throw them in if they are academic questions, industry questions, questions about what those cranes are doing over there. Those are all relevant.
Very good. So we can continue. Much of the teaching we do is informed by the research that's ongoing at ASU. And, ASU, one of the biggest schools in the country, we have probably the largest engineering program in the country. And so there's a lot of faculty research that's focused in this area of physical electronics and photonics. So the last class I taught about was solar cells, and we have capacity for, basically it's an industry standard pilot line for building solar cell modules and then incorporating the latest ideas that are developed in the R&D lab bench and bringing them over to see whether they're manufacturable for widespread deployment. We have fabulous what we call core facilities. So these are laboratories that allow researchers, both undergraduate and graduate students, to fabricate new types of devices, work with new materials, characterize those materials. And so this is a picture of our photolithography engineer, Carrie. She helps me with that 435 class. And here she is working with our optical aligner, which is one of the tools that students in that 435 class get to experience in a hands-on way, suiting up in this clean room suit going into the clean room. So photonics, a lot of work going on developing state-of-the-art solid-state lasers. So it's kind of interesting that we're focusing here on a white laser, because the idea of a laser is that it lasers, it produces light at just one frequency, whereas a white light source covers all the available frequencies. And so it turns out if we could have a white light laser, that would be very useful for high intensity, very high brightness TVs. So large commercial application there. And then one of the things that I've recently become very interested in is the use of wide bandgap and ultra wide bandgap material. So I talked about silicon technologies in CMOS. So silicon has a band gap of about 1.1 electron volts. Gallium nitride, silicon carbide, and now diamond. Diamond has a band gap of 5.5 electron volts. So we're thinking about a future where electronic chips are made using substrates that are based on diamond. So some very futuristic things that would enable ultra high temperature operation. Imagine you could build a microprocessor that worked at 500 degrees C. You could sort of drop it into a jet engine to see how that jet engine is functioning. So lots of faculty research in this area, and as I mentioned, that informs a lot of the teaching that we do. So I guess I've got about 5 or 10 more minutes before we move on to questions, but I wanted to talk about, what do engineers do in for jobs in semiconductor manufacturing and the semiconductor industry. So we mentioned circuit design, and again, if there's anybody in the audience today in that circuit design track, when you build a chip, the first thing you do is download your process design kit from the foundry. Well, that PDK has been developed by the engineers who really understand the ins and outs of the semiconductor processing in that foundry. And those PDKs are extremely complex documents, complex software tools, and those have been put together by the engineers who understand that semiconductor manufacturing technology. Simulation and modeling, I haven't talked a lot about this in those classes, but we have powerful TCAD tools, so technical computer aided design, TCAD tools, that allow us to design a chip all the way from the silicon to the final circuit. And that is the reason why companies like Intel and TSMC are so successful, is that they're able to simulate that entire process flow so that when they actually build the chip, there's a very good chance that it works first time without having to be re-engineered. And if you think that if you realize that a mask set to build chips is approaching $100 million, then you have to get that mask set correct from the beginning. Otherwise, you're having to redesign it at the cost of tens of millions of dollars. So simulation and modeling is very important. We talk about digital twins, right? So this is the idea that you have a foundry that you're building for $20 billion, but you have a model of that foundry that simulates every part of it. So you can see how the factory is going to work on your computer before you actually go ahead and build that chip that you're interested in. Then, of course, fabrication. We need the engineers in the clean room, in those manufacturing facilities, to make sure the equipment's working properly, design the next set of processes that will be used in the coming years, measure the devices. If you've got a transistor, if you've got a chip with 1 trillion transistors, how do you measure it to make sure that all the transistors are working? You can't, right? So you have to develop complex statistical models and the testing that's required to understand whether you're going to maintain the yield. Are 100% of your chips working when they come out of the pilot line? It won't be 100%, but you want it to be as close to 100% as possible. Measurement and characterization. I alluded to that. You've got 1 trillion transistors. How do you measure them? How do you characterize them? So we need special circuits designed to be able to confirm that all those transistors are working in the way we want. And then, of course, sales and marketing, right? We need people to explain to the customer what the capabilities are, and then the customer has to explain to the foundry what their needs are. So that's a very complex relationship. So we've all heard of the Intels and I've got, let me see, 5 more minutes, Bob?
Yeah, just about. And we have
Yeah.
one question to answer at the end.
Okay, so the public as a whole, we were always aware of Intel. There was that marketing campaign, Intel Inside, and we saw that everywhere. Now we've learned about TSMC because of all the politics of moving factories back onshore into America. But what about the companies that we've never heard about? What about the billion-dollar companies we've never heard about, right? Applied Materials. They make the machines that go into the clean rooms that the foundries use. And ASU just signed a deal for $230 million. Applied Materials are putting the latest state-of-the-art tools into our clean room on the Science Park. Look at this machine in the middle. This is the lithography tool from ASML. The New York Times a couple of years ago had a good article about how this is the most complex machine ever made. This is what the semiconductor manufacturers use to be able to pattern the chips at the sort of 2, 3, 4 nanometer level. This has now become a political animal. The US administration has forbidden this tool to be exported to. It's actually made by a company in the Netherlands, but the components come from everywhere. So you can get jobs in equipment manufacturing, circuit design, the communication providers, energy service providers, as well as the device manufacturing. So here's a list of the companies. I don't know, like I mentioned, we've heard of Intel, TSMC, you slap on the wrist, TSMC. NXP here in town, they're a big hire of our graduates. I mentioned Applied Materials, lots of other companies that support those manufacturers, and then also all the service companies that support the software design and updating. So lots of job opportunities. The jobs go with the sales. You can see here, it's kind of cyclical. There are sort of booms and busts. We're in the biggest boom that I've seen in a generation. And I think those jobs will be reflected in the coming sort of 6, 18 months. And a lot of that is this investment, Chips for America. So CHIPS is an acronym, creating helpful incentives for the production of semiconductors. This was a $52 billion investment by Congress. Think about that, $52 billion, it's enormous. So I will finish up there just by alluding to, you complete your graduate degree, your undergraduate degree. Well, what's next? Well, an MS degree is, I know TSMC is looking to hire lots of students who have completed a master's degree. And I'm sure Bob and his team will tell you about our 4+1 program. That's a very good way to get a master's degree in an accelerated lower cost option. And then a PhD, I've been hiring a lot of PhD students recently. It's a big commitment, right? Probably additional 3 or 4 years after your master's degree. If you're fascinated by the subject, that's a very satisfying career move. But again, it's that longer term commitment, staying at school. So I'll finish there, Bob, and take any questions.
Thanks very much for the presentation. Alex is just, this is great for any engineering student online. He's asking your opinion on lack of hands-on prep, how that affects an online student. I've got some thoughts on that, but what do you think about our online
that's
students?
a very good question. So Alex, right? So I teach that 435 class, and we cap the number of students. We bring 36 of them, 12 on each lab session into the clean room, and they get the hands-on experience of putting on our bunny suit and touching our tools and measuring things. Now, if you're an online student, we provide videos so that you can watch what the students are doing and understand what they're doing, but clearly you're not putting on the clean room suit yourself. Now, let me just take a step back, because TSMC approached us wanting to have more students experience this. And it's very clear that what we do in universities is about, if I'm being optimistic, we're 20 years behind what the industry does. So the clean room suit that our students put on is completely different to the one that TSMC engineers work in. The transistors we build in the clean room are completely different to the ones that TSMC. Likewise, our tools are completely different. So TSMC's response was, well, it doesn't matter. We will train our employees on the bleeding edge, state-of-the-art technology that we need. We just want the students to have an understanding of what it is they will be doing in the industry. So although as an online student, you're not in there touching things and putting on the clean room suit, you are aware of the need to have the clean room suit, of the types of tools that you will be using in those careers. So I totally accept that the hands-on piece is missing from the online, but the understanding is there, and that's really what's important for the industry. But good question, thank you.
Yeah, thanks. I pretty much agree with everything. A lot of it has to do with, too, from my perspective, is as an online student, you have to, the engagement part of what you do while you're a student isn't kind of in your face like it is for a student on campus. And there's ways to engage and participate outside of classroom in your academic areas. You just have to make it happen sometimes. But showing up to a seminar like this is a good example of a way to engage as an online student, just to hear it outside of the classroom. Thank you. That was we don't have additional questions there. And I know Professor Wu is here ready to talk about the power area.
Very good. I'll stop sharing, and thank you all the students who showed up. If you have any questions, you can find my email online and I'll be happy to respond to those. So thank you, Bob. Thanks, Cheryl, and everybody.
Thank you so much
again.
for
Thanks
coming
for being
today.
here.
It was great.
Thanks. Yeah. Bye-bye.
Bye.
Great, and students don't leave yet because the power area is here, and Professor Meng Wu is here, and she has a presentation she's sharing. So thanks very much for being here, Professor Wu, and please go ahead and present as soon as you're ready.
Yeah, thank you, Robert, for the introduction. Can everybody see my screen?
Yeah, you're not in presenter mode, but that's up to you.
Okay, yeah, I can go to the presenter
There
mode.
you go. Looks great. Thank you very much.
Okay, so good morning, everybody. My name is Meng Wu. I'm an assistant professor in the Electric Power and Energy System EPES program at ASU. So basically today I'm gonna do a kind of overview, overview of what Electric Power and Energy System program does and what is the expected courses in this program, and how is the job opportunities and future career opportunities in this area. So essentially, this is an overview of the Electric Power and Energy Systems program at ASU. So our Energy Power System program at ASU is actually one of the largest power energy programs in US today, and it's gonna be it's among the top 3 programs in the nation in terms of research excellence and recognition. So we have actually 3 faculty and members in this program who are National Academy of Engineering fellows. So that's the kind of highest honor you can get as a researcher in the engineering area. And also the most different thing of the power area in ASU is that we actually have the kind of most diverse research areas and simulation tools, laboratories, and all kinds of hardware and software capabilities for carrying out different types of experiments. And also our students, both undergrad and grad students, have very excellent record with our employers. And also undergrad students, a lot of them are being placed in very good grad school programs, master's and PhD programs in ASU and out of ASU across the nation. And also there are also excellent employment opportunities in the power area. For example, in conventional kind of traditional power system area, the typical career path will be you can join a utility company, for example, the APS and SRP, who are the local utility company in Arizona. And also you can join a software or hardware vendor company for power area. For example, General Electric GE is a both hardware vendor company for power electronics devices, and also like wind turbines, and also software vendor company for different types of computation softwares in power area. And also like Siemens, which is a software vendor for the power area. And also if you're working on power electronics, there are also opportunities working on like Tesla, which is making a vendor of electric vehicles, which use a lot of power electronics techniques, and also there are actually recent employment opportunities in power area currently are actually expanding, because there are a lot of companies that are putting money into like investigating how power system will be impacting the climate change in the future. So, for example, Microsoft and several other big companies like Google, they are and also Amazon, they are putting money into basically investigating how machine learning and AI can help the power area decarbonize the power area, and also decarbonize the entire society to basically mitigate the impact of climate change. So the employment opportunities are actually growing in the power area due to the climate change and the decarbonization. So this is a list of power area faculty members in our in ASU program. So Dr. Raja Anar, he's an expert in power electronics, working on power electronics. And Dr. Corey Hetman is an expert in electricity market. And also Dr. Jerry Hyde is a expert in power quality and also other power system operational research related topics. And Dr. Keith Holbert is an expert in nuclear power plants. So if anybody is interested in nuclear power plant, there is a dedicated faculty member here who is working on nuclear. And also Dr. Mujay Borsan, she's an expert in distribution, low voltage power system, and also electricity market. And Dr. Chin Lei is also working on power electronics. Dr. Anamitra Paul is working on the measurement system for large-scale power systems, and also he's doing a lot of work in data-driven and machine learning techniques applied to power systems. And Dr. Mike Rangel, he's also working in the power electronics domain. So if you guys, anybody is interested in, say, works done by Tesla, then power electronics could be a good direction to pursue. And also Dr. Amar Reddy. So he is a professor that is working on voltage stability of large-scale power systems. And also Dr. Lalisa Sankar, she's working on the cybersecurity aspect of power systems. And also she's also doing a lot of work in communication engineering and also machine learning, data-driven applications. And also that Dr. Daniel Talovsky, he's working on a lot of issues about large-scale computation, how to reduce computation burden for large-scale power systems. And Dr. Vijay Vital, he's a expert in stability and dynamics of power systems. And Dr. Yang Weng, he is working on machine learning applications on power system. And also me, so I'm working also on distributed energy resources, and also how to integrate distributed energy resources into the large-scale power systems using optimization and data-driven machine learning approaches. So basically, Dr. Jerry Hyde and Dr. Vijay Vital on this slide, they are both NIE, National Academy of Engineering members, which is the kind of the highest honor we can get as engineers. So this is a list of undergrad courses in the power area. So starting from the entry-level course, which is EEE 360. So this should be the entry-level course everybody should take if you are in power engineering concentration. And then on top of that 360, we have branching out topics into different areas. For example, we have nuclear power engineering courses, and also we have courses on electric power plants and electric power devices, power system analysis. So basically EEE 470 and 471, I will be teaching these two courses. They are going to be giving you a fundamental knowledge for how large-scale power system will be operated and will be planned. So these are kind of fundamental courses in this area. And then if you're interested in power electronics, then EEE 472 power electronics will be the kind of fundamental courses in that area. And also we will have electrical machinery, which is talking about the design of AC and DC machines, which is also going to be useful for related to power electronics topics. And also we will also, as other areas, we will also have senior design projects that spans across your very final year, the 4th year of your undergrad study. So if you are in the concentration of electrical power and energy system, there are some special requirements for this composition, which is first, you will need to take EEE 360, which is the first step, the entry-level course for the power area. And then on top of 360, you will need to take an additional 9 hours, that is roughly 3 courses of power area courses. So those will be your 4, basically all these 460 or 470 some courses that will be counting toward those 9 credits. And then of course you will have a senior design capstone, senior design projects that is related to the energy power system study field approved by basically by the department. So these are the course selections for satisfying requirements in power area. And then basically we have different technical elective, different 400 level courses under power system, under this power area. So basically, essentially these courses falls under 3 different categories. So we have courses talking about things related to power generation. And we have courses related to transmission and distribution system. And also we have courses related to electricity utilization. So basically that covers all the areas that will be useful for power systems, starting from how do we make electricity, how do we generate electricity, to how do we send electricity from generation to customers, and then to all the way to how does customers utilize electricities. So this is the coverage of all the technical elective 400 level courses we have. So basically, if you are interested in, say, manufacturing companies such as GE, who is making motors, who is making wind turbines, then you might be interested in taking power generation related courses. And if you're interested in like software vendors such as transmission distribution system analysis softwares, then you may want to take courses in transmission and distribution area. And then if you are interested in, say, Tesla, then that is related to power electronics, which is majorly falls under this electricity utilization kind of area. So our power system courses are not really only kind of useful in large-scale power system, but also small-scale power systems, such as if you consider the power system in an airplane or in a ship. So those are small-scale mobile power systems, and all the knowledges that you learn out of the power area courses and senior designs will be also useful and can be applied to designing and operating power systems for aircraft and ships. So if you're interested in working job opportunities in those areas, so those are the information that can be helpful for those job opportunities also. So basically, there are several major kind of changes that the power system are, our electric power system are currently facing. One, basically the driving factor is essentially first the climate change. Is basically everybody knows that our temperature is gradually increasing year by year. So the climate is really changing, and we are expecting more like natural disasters across the year. So how to kind of rebuild our power system to allow more renewable energy to really decarbonize the entire society and slow down the climate change, and also help our system defend themselves against the different kinds of natural disasters. Those are several major driving factors for renovations and transformations in the power industry. These are not only happening in research domain, but also in manufacturing domain, such as like there are more companies that are trying to adopt and build wind turbines, solar panels, and also like Tesla, which is a vendor of electric vehicles. So these new job opportunities are all coming out of this renewable energy trend, and which is driven by slowing down climate change. So basically, these are several courses related to power generation. Essentially, if you are interested in manufacturing of wind turbine and solar panel, and also conventional power plants. So these are the course that will cover those topics: electric power plants, EEE 463, and nuclear power engineering, EEE 460, which is so this EEE 460 is focused on a special technique, which is the nuclear power plant technique. And also, if you are interested in transmission and distribution systems, then these are the courses that are covered in knowledge about transmission distribution system, electric power devices, and power system analysis. Essentially, these are going to cover all the knowledge you need if you want to work in a like GE or Siemens or other like vendor or consulting companies that are making commutation softwares or relays or circuit breakers, or if they are like running consulting business in the transmission and distribution area, or like a research lab that are sponsored by Microsoft, who are doing the climate change study for decarbonizing the electric power grid. So essentially, all these two courses will be one major focus of these two courses is going to be basically tell students how we can kind of strengthen our electric power grid against the different types of disasters or unstable events. So this picture actually shows a very famous blackout event that is happened, I believe, in 2003 in the northeast part of US and also southeast part of Canada. So this is a very major blackout event that actually spans across several states, causing loss of electricity to like around 55 million people in the most populated area in US, such as New York and New Jersey and Michigan and Ohio, these areas. And this major event lasts for like 2 hours to 4 days, depending on where you are located. So the longest power outage caused by this event is actually a 4-day power outage. And also, it also caused almost 100 people, 100 deaths across out of this little single event. So this is actually this event, the cause of this event is very simple, very naive. It's just a tree that is growing too tall, and it grows into a transmission line. So that tree touching the transmission line which caused a short circuit in the transmission system. And that short circuit actually was not really captured by the monitoring system because there is a bug in the false alarm in the monitoring system. So the system operator didn't really pay attention to that small event, local event. And then that local event will propagate across the system because no one is paying attention, and eventually it brings down the entire power grid for the northeastern part of US and also southeastern part of Canada. It's like a tree growing too tall causes like 55 million people losing power and causing 100 people death. So basically, in these two courses, we'll be learning fundamental knowledge about how we can design our system to prevent this kind of bad event from happening again, and also how we can operate our system when we see this kind of event to save the system from having a very bad kind of blackout, major blackout. So if you are basically interested in power electronics, these are the courses related to power electronics. We have 472 power electronics and also 473 electrical machinery. Basically, these are going to be giving you information on DC DC motors, and also how do you convert DC to AC or AC to DC through power electronics. So basically, there are a lot of applications for power electronics in terms of job and research opportunities. For example, we mentioned Tesla several times, which is going to be the manufacturer of your electric vehicle. So within the electric vehicle and also the batteries that are being produced by Tesla, there will be AC-DC converters, which are going to be your power electronics semiconductor devices. And also, if you are talking about a Google data center, these are also DC kind of power consumption. And they need to be connected to the grid through AC-DC converter. Again, that's the power electronics part of the Google data center. And also, there are also many other applications of power electronics. So these are several sample senior design projects that are being done in the past several years by supervised by different advisors, different professors in this area. Basically, if anybody is in the power concentration, you will need to get a senior design project with a power area professor. So taking several examples, like this one, supervised by Dr. Corey Hetman, is about is a study done for ERCOT, which is the power system operator for Texas. So their major interest is how to manage their Bitcoin mining load. So they have a lot of Bitcoin mining companies in Texas, and they are consuming a huge amount of power. So the system operator is trying to study how can they combine this Bitcoin mining load and their solar farm to basically better serve the grid and save electricity bill, and also make the power system more healthy for Texas. And also we have a senior design project on DR, distributed energy resource management, and also smart grid. And also we have other power electronics related studies. For example, how do you integrate solar panel into your systems, and also other portable power supply. So these are possible senior design topics in the past several years. So this basically if anybody is interested in research opportunities, for example, pursuing like a master's or PhD degrees in the power area. So these are several major investigation areas, research areas in power system. Basically, all these new investigations are driven by, again, decarbonization and climate change that is happening today across the nation. So essentially, we are changing our power system from this centralized generation using like fossil fuel power plants, such as coal power plant, gas power plant, and other types of basically fossil fuel power plants, to a more smarter and greener power system with distributed energy resources, such as these rooftop solar panels, and also with utility. So this is utility scale battery power plant that is being built by Tesla. So this is a Tesla power bank, which is, again, the so-called inverter-based resources that is connected to the system through power electronics, AC and DC conversions. So this kind of paradigm shift is actually driving a lot of innovations in both research areas and also the industry applications. So it is not, the opportunity is not just limited into power area, but also there is an intersection between power area and also like communication and IT areas. For example, people are looking at cybersecurity solutions for power system. How do you transmit data securely for operating your power system? So this is an intersection between communication and power. And also a lot of people now are working on how do you leverage AI and machine learning techniques to help power system better transform from this fossil fuel-based generation to more smarter and greener, like distributed energy resources, and also utility scale renewable energy. So ASU is also a leading university of several large research centers. So we have PSERC, Power System Engineering Research Center. So this is a major research center with 13 universities and 36 industry partners. And ASU is basically the leading technique for this particular center. It's the leading university for this particular center. And also for students, this PSERC center do offer like regular kind of webinar series that students can join and listen to the presentations and know what is the cutting edge research and engineering needs in this area. And also there will be like on both virtual and in-person kind of job interview opportunities and career fair opportunities that is provided by Power System Engineering Research Center. And also there is an online platform for students to submit their CVs or resumes, and the partnering industry companies, if they have some opening, they can look up the submitted CV and resume. If they find a match candidate, they will be able to contact that candidate through email. So basically, if you're interested in more of job and webinar and research opportunities under the center, just click this link and you will be able to find all the information, and you can basically register an account using your ASU student email address, and then you will receive regular kind of updates from the PSERC center. And also there's another center, EVSTS. So this is more about electric vehicles and transportation system. It's an intersection between power system and also the transportation. Basically, if you're interested in Tesla or say electric vehicle, this could potentially be a good venue. And also we have different power related labs. So these are basically a figure of our power, a picture of our power electronics lab. Other than this power electronics lab, we also have high voltage lab and also power system simulation lab, and also other types of labs on campus, which basically provide students hands-on experience for working on both hardware and software of power system, commercial kind of hardware and software in power system, and also power electronics. So this is another picture of our synchrophaser lab, the measurement technique lab, and also a machine learning lab in power systems. So I think these are all I have, and I'm gonna stop here and ready for questions.
Yeah, thanks very much, Professor Wu. One student, Ben, is asking your opinion on if he's interested in the construction side and of power, what classes would you recommend? I assume there's a few different ways to answer that. The courses in the power area that we have at the undergraduate level may not get specifically into the construction industry specifically, but or more of an overview. I know we have courses in nuclear power, electric power plants that might be relevant to construction devices, and it kind of specializes. Do you have any thoughts on that question, Professor Wu?
Yeah, I think essentially you're correct. Basically, electric power plants and nuclear power engineering are more of an overview of the techniques on the electric power side of power plant. But basically, these are going to be still helpful, because even if you're working on the construction, there are some fundamental knowledges like how do you compute like the capacity and different types of things that will be covered under these topics. And also power system analysis will also be something useful for running different types of electrical calculations to figure out what type of power plant you want to build. and also electrical machinery may also be helpful to figure out basically different types of machines. For example, synchronous machine, or if you're constructing a wind farm, then that will be an induction motor. So these are different types of machine techniques that could be also helpful. So on the mechanical part of the construction, if that is the interest, then maybe you can take a look at courses offered under mechanical engineering. I believe there might be some interesting courses in that area. But our course currently is more focused on the electrical part of power plant.
Yeah, thanks very much. Yeah, a lot of our students work in many different industries. Electrical engineering is quite broad, and so it's kind of a springboard for all of those. But yeah, thanks for that question, Ben. That was great. Are there other questions for Professor Wu, or any questions for the advising staff who are online today about curriculum or anything like that? Okay, James is asking, oh, James, yeah, we will have this on our website. There's usually about a week delay. Does someone mind posting the link into the chat? I always struggle to find that link while I'm talking. So I'm sure we'll put that there. So we record them, and we will post all of them. So if you miss any of these seminars and you want to watch them, we'll have the link in this chat before we're done here.
And in the meantime, before the new ones posted, we have some older versions posted that are good to watch too.
Yeah, thanks. Thanks, James, for asking that. Thanks, Gia. So yeah, the link's in there, and sometimes there's some older ones, and sometimes we don't update them because we like the older one better. But this was awesome because Professor Wu knocked it out of the park, so we should put this one on there.
Yes, absolutely.
Well, if there aren't any other questions, we'll go ahead and wrap up. It's just about time anyway. So thanks, students, for being here. Online students, we love when you attend this. It's great to have a live event with you. So thanks for taking time out of your work days or family days for this. Professor Wu, thanks very much for your informative presentation. We really appreciate your time.
Thank you very much.
Thank you.